Specific heating. Specific heat is defined as the energy required to rise by 1 degree temperature of a unit mass of a substance. In general, this energy depends on how the process is run. In thermodynamics, the focus is on two specific heat classes: specific heat at constant volume Cv and specific heat at constant pressure Cp. Why Cv greater than Cp? Because at constant pressure the system is allowed to expand, and the energy for dissipation work must also be supplied to the system. The specific terms in terms of other thermodynamics properties. Energy that goes in less the energy that comes out is equal to the energy of the system. The left side of this equation represents the net amount of energy transferred to the system. From the definition of Cv, this energy must be equal to Cv per dt, where dt is the differential temperature change. So Cv per dt is equal variation of internal energy. It will be more appropriate to define Cv as change in the internal energy of a substance by unitary change of temperature to constant volume. Also, it is possible to define Cp as change in the enthalpy of a substance by unitary change in temperature at constant pressure. In other words, Cv is a measure of the internal energy variation of a substance with temperature, and Cp is a measure of the enthalpy change of a substance with temperature. Units for specific heat is kilojoule on kilogram per Celsius degree or kilojoule on kilogram per Kelvin degree. Note that both units are identical signs. Variation the temperature of Celsius degree is equal variation the temperature of Kelvin degree, and a change of 1 Celsius degree in temperature is equivalent to a change of 1 Kelvin degree. Sometimes the specific heats are given on a molar basis. In the case they are denoted by Cv with a line up and Cp with a line up, and have the unit kilojoule on kilomole per Celsius degree or kilojoule on kilomole per Kelvin degree.
Internal energy, enthalpy, and specific heats of gases ideal. An ideal gas is defined as a gas whose temperature, pressure, and specific volume are related by pressure by a specific volume is equal to the universal constant of the gas given by the temperature. In his classical experiment, Joule submerged tanks connected with a pipe in a valve in a water bath, as shown in figure. Initially, one tank contained air at a high pressure and the other tank was awakened. When thermal equilibrium was attained, he opened the valve to let air pass from one tank to the other until the pressure equalized. Joule observed no change in the temperature of the water bath and assumed that no heat was transferred to or from the air. Since there was also no work done, he concluded that the internal energy of the air did not change even though the volume and the pressure changed. Therefore, he reasoned that internal energy is a function of temperature only and not a function of pressure or volume. Internal energy. The internal energy, according to the first principle of thermodynamics, is understood as linked to the random movement of particles within a system. Internal energy variation. The internal energy of particle systems can vary, regardless of their spatial position of accurate form, in the case of liquids and gases. For example, by introducing heat to the closed system of particles, thermal energy is added which will affect the internal energy of the whole. However, the internal energy is a state function. That is, it does not attend to the variation that constitutes state of matter, but to the initial and final state of the same. That is why the calculation of the variation of the internal energy in a given cycle will always be zero, since the initial state and the final state are one and the same. The formulation to calculate this variation are: variation of the internal energy is equal to the internal energy in B minus the internal energy in A, where the system has gone from state A to state B. Variation of internal energy equals less work, in case where a quantity of mechanical work is performed, which results in the expansion of the system and the decrease of internal energy. Variation of internal energy is equal to heat, in case where we add caloric energy that increase to the internal energy. Variation of the internal energy is equal to zero, in case of cyclical change of internal energy. All these cases and others can be summarized in an equation that describes the energy conservation principle in the system. Variation of internal energy is equal to the heat more work. Examples of internal energy: batteries, compressed gases, when increasing the temperature of the matter, when shaking a liquid water vapor. Now an exercise of isobaric process. A gas has a volume of 2.1 cubic meters and 2 kilopascal of pressure is subjected to an isobaric expansion process until the volume increases by 80%. To carry out this process, 7,800 joules of heat must be added to the system. Determine the internal energy change that the gas undergoes. To solve this exercise, as a first step we must take into account the concept of the first law of thermodynamics, internal energy, and what is an isobaric process. Well, an isobaric process refers to a process whose pressure is constant. Next, we propose the graph and the equation. In this case, we have a system which when supplying heat is going to be positive, and when removing heat it will be negative. It makes a lot of sense, because if I inject air into the system, the temperature increases and therefore the internal energy. The same will happen if I remove the heat. Similarly, when you perform work on the system, it will tend to be negative. The graph shows an initial volume or volume 1 and a final volume or volume 2. Likewise, the pressures are the same, since it is an isobaric process. In addition, the work is equal to the pressure due to the volume variation. That is, the final volume minus the initial volume. The initial volume is 2.1 cubic meters, which is the volume they give me in the exercise, and volume 2 is 1.8 of volume 1. Since they speak to me of an increase to 80 by the way, that is 180%. The pressures are going to be the same. Since it is isobaric and the heat is 7,800 joules. All the data collected above I will serve to apply in the formula. Work is equal to pressure by volume variation. Then we define 2000 Pascal multiplying to 1.8 the volume 1 minus the volume 1. It is equal to 2000 Pascal per 0.8 the volume 1. I replace data, I operate, and I leave 3360 joules. That is, my work is such a result. Once I have this information, I apply the formula of the variation of the internal energy, that is the heat minus the work. The heat is already given to me, 7,800 joules, and the work is what I have found. I mean 3,360 joules. Resin finds that the variation of internal energy is equal to 4,440 joules.
Internal energy, enthalpy, and specific heats of solids and liquids. A substance whose specific volume is constant is called incompressible substance. The specific volume of solids and liquids essentially remains constant during the process. For solids and liquids, The subscripts on Cp and Cv can be dropped and both specific heats can be represented by a single symbol C. Internal energy changes. Like those of ideal gases, the specific heats of incompressible substance depend on temperature only. Thus, the partial differential in the defining equation of Cv can be replaced by ordinary differential, which yields the equation number 1. The change in internal energy between states 1 and 2 is then obtained by integration, and that results the equation number 2. The variation of a specific heat with temperature should be known before this integration can be carried out. For small temperature intervals, a C-value at the average temperature can be used and treated as a constant, yielding the equation number 3. Enthalpy changes. Using the definition of enthalpy, enthalpy is equal to the internal energy plus the pressure per volume, and noting that the volume is constant, the differential form of the enthalpy change is of incompressible substance can be determined by differentiation. Integrating, the variation of enthalpy is equal to the variation of internal energy plus the volume per the variation of the pressure. For solids, the term volume per the variation of pressure is insignificant, and thus the variation of enthalpy is equal to the variation of internal energy. For liquids, there are two special cases. First, constant pressure process, as in a heaters, where the differential of pressure is 0. Then, the variation of enthalpy is equal to the variation of internal energy. Second, constant temperature process, as in a pumps, where the variation of temperature is 0. The variation of enthalpy is equal to the volume per the variation of pressure. To understand more about the topic, let's see one example. A 50 kilograms iron block at 80 Celsius degree is dropped into an insulated tank that contains 0.5 cubic meters of liquid water at 25 Celsius degrees. Determine the temperature when thermal equilibrium is reached. Solution. An iron block is dropped into water in an insulated tank. The final temperature when the thermal equilibrium is reached is to be determined. For this problem, let's make some assumptions. First, both water and the iron block are incompressible substances. Second, constant specific heat at room temperature can be used for water and the iron. Third, the system is stationary, and thus the kinetic and potential energy changes are 0. Fourth, there are no electrical shaft or other forms of work involved. And 5. The system is well isolated and thus there is no heat transfer. We take the entire contents of the tank as the system. This is a closed system, since no mass crosses the system boundary during the process. We observe that the volume of a rigid tank is constant, and thus there is no boundary work. But there not exists work, heat transfer, and the system is stationary. Therefore, the variation of internal energy is equal to 0. The energy balance on the system can be expressed as the energy in less the energy out is equal to the variation of the energy of the system. The total internal energy is an extensive property, and therefore it can be expressed as the sum of the internal energies of the part of the system. Then The total internal energy change of the system becomes the variation of the internal energy of iron plus the variation of the internal energy of water. Then we know that the variation of internal energy of the iron and the variation of internal energy of the water is equal to its mass per its specific heat and the variation of the temperatures. The specific volume of liquid water at or about room temperature can be taken to be 0.001 cubic meters per kilogram. Then the mass of the water is 500 kilograms. The specific heats of iron and liquid water are determined from table A3. The specific heat of iron is 0.45 kilojoule over kilograms per Celsius degree, and the specific heat of water is 4.18 kilojoules over kilogram per Celsius degree. Substituting these values into the energy equation, we obtain the final temperature that is 25.6 Celsius degrees. Therefore, the thermal equilibrium is established. Both the water and the iron will be at 25.6 Celsius degree. Therefore, when thermal equilibrium is established, both the water and the iron will be at 25.6 Celsius degrees.